Good day, everyone. My name is Rebecca Lilly for the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled Comprehensive Life Cycle Analysis of Generation Technologies. First, a little bit about the International Association for Energy Economics. We're the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations along with a host of other products and services that you can find on our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speakers. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the speakers, please click the Q&A button at the bottom of the Zoom window and type your question. We've allocated sufficient time at the end of the webinar to address your questions. And now I would like to introduce you to our speakers, Dr. Gershon Gulen, Principal at G2 Energy Insights, and Dr. Michael Young, Senior Research Scientist at the Bureau of Economic Geology at UT Austin. Gershon, over to you.
Thank you, Rebecca. Let me share my screen. And hopefully everybody is able to see the title slide. So I'll get started just quickly. Rebecca introduced me as the principal of G2 Energy Insights, but I'm also a researcher at the Bureau of Economic Geology. And so I'm wearing multiple hats. And Michael is also a senior researcher at the Bureau of Economic Geology. And we're going to present this together. I'm going to get things started. And so this is to set the stage. Why are we conducting a LCA, life cycle analysis? My assumption was that everybody is kind of familiar with the concept of life cycle analysis, if not the details of it. If that is not the case, let us know. We can try to explain it in more detail. But as we go through the presentation, it should become clear, even if you're not well versed on what an LCA is. But in a nutshell, is looking at environmental impacts associated with different activities. This could be done for any industry. Of course, our focus is the energy industry and in particular power generation technologies. And this slide is about the rationale for conducting this research. The LCA is the main tool that we're using for comparison of electricity options program. This is a relatively new research program at the Bureau of Economic Geology at UT Austin. And we'll give you the details going forward, but we're looking at energy generation technologies, not all of them, a select few. And we're looking at total life cycle from extraction of natural resources, processing of minerals, natural gas, manufacturing of equipment, building the power plants, operating the power plants, and end of life. So why do we care about this? Well, we do care about this for kind of the reasons that you see on the slide. Globally speaking, my number is always about 6 billion, but 5, 6, 7, whatever number you want to pick, there is a large number of people without access to modern energy services. And I did give a presentation on this for IAE on energy poverty last year, or maybe a year and a half ago. If you're interested, please get in touch with me and I'll give you the link. And we are going through an energy transition, if you want to call it, but at the same time, an energy expansion. We're developing a lot of capacity for power generation, as well as other segments of the energy industry, but we are focusing on the power generation today. And of course, wind, solar, geothermal, all of these things are growing in capacity, but we're not ignoring all technologies either. They all seem to be needed, to meet the growing demand. And rapid deployment of some of the newer technologies, new being a relative term here, exposes some challenges along the supply chains, and of course, some environmental externalities. ESG concept, environment, social governance, is the newest form of what maybe in the past people talked about as corporate social responsibility and different terms similar to that. So the new term is ESG. Energy security and affordability of energy are not easily reconciled for the reasons that you see. Towards the end of the presentation, we'll get back to levelized cost of electricity and why it is, an inadequate metric to look at full system costs. And I did have a podcast for the USAE on that based on a report I did write in 2019. So that link will be available later in the slides. And externalities are not systematically priced, right? So that's an economist idea of how to price externalities, and therefore the decisions can be made based on price signals. That's just not happening. So ultimately, the way I like to think about this is a whack-a-mole problem. We're trying to, address all of these issues, but when we try to fix one, there is something else popping up from somewhere else. So it's a challenging, multidimensional problem space. And the way we think about it, a comprehensive life cycle analysis is a necessary input, although not sufficient by itself, to inform at least the E and increasingly S, so environment and social aspects in the ESG framework. And it is also useful and necessary to price externalities. So that's kind of the rationale. Based on that rationale, for very specific purposes of our project, we did ask this question: how can we provide reliable and affordable electricity while mitigating climate change concerns, but also mitigating local environmental impacts? This is just another way of, putting the problem as we discussed in the previous slide. So far, we did do quite a bit of work in almost a year. And our results so far are showing, if you don't get through all the slides, at least you have this key takeaway slide. So it is important to look at all impacts, certainly climate change, but other emissions and other emissions to the air, land and land use and ecosystem services and biodiversity is becoming a key topic in the area of land use, and as well as water use and water pollution. So, and we'll show you some metrics on how the literature has been addressing these issues. There's a lot of LCA work out there, if you're familiar with any of it, and but a lot of it focuses on maybe not the full value chain or full supply chain. They might be focusing on, let's say, power plant operations. We are looking at the cradle to grave space, all the way from extraction of the resources and end of life of the power plant. And we'll show you some slides that will hopefully explain this a little bit better. And the results are very sensitive to assumptions on operational parameters, and as well as the assumptions about the life of an asset. So, and operational parameters are things like, conversion efficiency in thermal plants, or capacity factor of wind or solar generation facilities, which is highly dependent on location. And of course, the grid issues. And the asset life, some of these assets can operate for 50 years. Some of them maybe are not going to last that long, maybe as short as 15, 20 years. So considering when and where the impacts occur and their pathways is very important. And we look at per unit impacts. And in our case, the unit is going to be megawatt hours of electricity generation. This is a typical approach in a life cycle analysis, but we do also look at the total impacts. The reason for that is you replace or build a lot of something new, and to replace maybe something existing, there is a lot of front-end impacts. So that front-end loading of impacts is an important concept. And then, of course, looking at these things, ultimately the goal is to identify weak links in the supply chain and what can be done to mitigate at least some of these impacts, so that, we address that, part of the guiding question, like reducing emissions or environmental impacts, and while making things as affordable as possible. And our results should inform the ESG standards. Right now, the ESG space is very messy. There are more than 70 agencies that provide some kind of ESG rating, but the academic literature is, to say the least, is inconclusive whether the ESG ratings correlate to, financial performance of companies, which ultimately is the goal of ESG ratings, right? To encourage people to improve their operations from an environmental, social, and governance perspective, while still generating return to their shareholders. So, and finally, incorporating these, the economic cost of these impacts, as well as system integration cost, will hopefully lead to a metric that is much more useful than levelized cost of electricity to assess alternative power system scenarios. That's kind of the high level conclusions based on the ongoing research and based on the past research that we have undertaken. This is just to remind everybody that, all the international agencies or USGS included have published reports, and you probably read now increasingly in the mass media that rapid deployment of wind, solar, batteries, not only for power generation, but also in the case of batteries for transportation sector, we're already starting to see some increased commodity price volatility and supply chain bottlenecks and geopolitical considerations that are pushing governments to bring back, for example, mining operations or battery manufacturing back to Europe or back to US. So Biden administration has these policies, for example, to increase mining for lithium and rare earths, and also increase battery manufacturing in the US. So all of these considerations lead to already, some of the issues that oil and gas industry is familiar with, but now the mining industry seems to be facing similar challenges, although at a lower scale. For example, opening a mine in different parts of the US is facing local opposition because people are concerned about environmental impacts and things like that. So that's one of the drivers of the work that we're undertaking. So this is our definition of the supply chain, as I verbally tried to define earlier. So we're looking at the sourcing, which means extraction of natural resources. This includes copper, cobalt, lithium, rare earth minerals, magnesium, nickel, graphite, all the critical materials that you can see in the reports that I showed you in the previous slide. And then there's the processing of the ore or natural gas. And then there's the manufacturing of the equipment that is necessary to build the generation facilities, gas turbines, solar panels, turbine equipment for wind turbines, and so on. And then, of course, you build and operate the generation plant, and there are impacts associated with the operational life of the asset. And then there's at the end of life, what happens to all that power plant pieces and parts. So we're looking at all of these things. Another way to look at that problem space is in reference to the scope 1, 2, and 3, which I suspect many of the people in the audience are familiar with. These are discussed typically within the greenhouse gas emissions or climate change space, but ultimately they apply to all other environmental impacts. So scope 1 typically refers to operational life of the asset, and scope 2 and 3 are either upstream or downstream from the operation asset. So in our terminology from the previous slides, so upstream would be sourcing, processing, and manufacturing, and downstream would be end of life. So, and on this slide, you see that we do assume a 30-year life. This is again a part of a standard practice for an LCA analysis. To compare different technologies, you may end up assuming the same life for consistency purposes, but we are also testing the sensitivity of the life of an asset, as I mentioned earlier. A wind farm, if it's going to operate only 20 years versus a solar farm, which is going to operate maybe 25 years versus a CCGT that might operate 40 years. So over their lifetime, the impacts are going to be different because there's going to be some replacement of the capacity to maintain the operations for the same duration, for example. So these are some of the complications that we are trying to address. This is just a high level, if you like, list of impacts we're looking at. And we actually look at, I believe, 17 individual impacts. Some of them fall under these categories, right? So global warming potential is one by itself, but under biodiversity and ecosystem services, I think we have several different factors. And there could be some overlaps the way people group some of these impacts. This is our approach. So with life cycle analysis, there are packages, software packages that one can use, and there are also data packages one can use. But as we look at the global supply chains, sometimes we discover that there are shortcomings in terms of relevance of the existing databases in terms of their impact inputs in different locations, because a lot of databases are based on mostly European or OECD country operations of different types of industrial facilities. So when you go to mining operations or processing plants or manufacturing facilities in other parts of the world, those kind of impact inputs are not necessarily consistent. So we have been chasing down mining companies and some industry associations such as the Global Nickel Institute, Copper Institute, Cobalt Institute, and we've been collaborating with some consultancies that focus on some of these technologies such as battery manufacturing. So we've been doing our best to get first, primary data to update some of the assumptions. So far, what we have done is Michael will take over shortly and start going through some of our results. We look at several key materials and several key generation technologies. CCGT and wind are complete. We're looking at solar and battery. So we're not going to present you much on solar and batteries today, but that's ongoing work. And then soon enough, by the end of this year, we will switch to this purple circle when we will look at the whole power system rather than looking at individual generation technologies, which is the current focus. We're going to start looking at the overall power system, because a grid operation to be reliable, you're going to need real-time balancing of demand and supply. And that requires some transmission and distribution network and real-time balancing operations, which is going to have some implications in terms of the total infrastructure that needs to be developed. So, and we'll say a little bit more on that towards the end of the presentation. So this is what we started with. We're going to compare a combined cycle gas turbine and with a wind generation, as well as wind plus battery generation and solar generation plus, and finally solar plus battery. And all of these technologies are designed, or their capacities are identified based on their ability to generate 3 terawatt hours per year. And as you all know, wind generation and solar generation are not dispatchable by themselves. They will be generating electricity whenever wind and sun are available. But you can approach dispatchability of a CCGT by adding batteries to these systems. And that's what we try to approximate in those scenarios. So that's one of those improvements we think we are bringing to this type of analysis. Dispatchability is a very important criteria for balancing electricity grids. But again, this by itself is not going to be enough. We need to do the dispatch modeling in phase 2 of our research. So with that background, I'll turn it over to Michael to talk about some of the preliminary results.
Thank you, Gurjan, and welcome everybody. So as Gurjan mentioned, we are already doing some of these comparisons between wind, CCGT, with and without batteries. We're halfway through solar, but we don't have the results yet. So we have also been looking at a number of kind of critical materials, including lithium and cobalt, which I'll talk about today. And these analyses generate a tremendous amount of data and information, and just trying to account for the nuance of what the results show is by itself challenging. And so there's just not enough time to show everything. So these are the areas that we're going to talk about today: the LCA for lithium and cobalt supply chain, which was just completed by 2 master students at UT Austin who just graduated a couple of weeks ago. We will be doing a side-by-side comparison of the CCGT and wind. We'll be looking at the estimated greenhouse gas emissions for different transition scenarios. In other words, if we're going to retire coal and CCGT, how does the speed of the transition alter what the what the effects are going to be? Because as Gurjan mentioned, because we need to front load the environmental impacts from renewables, that causes a higher impact in a shorter time period. And then finally, impacts other than GWP are also being collected for PV solar, but we just don't have those data ready yet. Okay, next slide, please. So here are the 2 critical materials that we'll be looking at: lithium and cobalt. Next slide. Zach Harner, who was focusing on lithium, it looked at really different scenarios. And so this is a global map, obviously, of where lithium is sourced, where it is typically processed, and then where it is incorporated and deployed for generating electricity. And in this case, most of the lithium is used for batteries. So our traditional scenario is to have the mining and the recovery of lithium in Chile and Australia. It then becomes transported over the ocean to China, where it is primarily refined. I think 80 to 90% of lithium refining is actually in China. So this is not a stretch. Cathode production is the same, so we would be creating cathodes in China, and then ultimately incorporated into batteries and other technologies, which are then shipped back over to the U.S. Now, this we don't have it listed here, but I think that the transportation distance is somewhere between 30 and 40,000 kilometers. So it's a long distance for the material. If we were to go to the next slide, please, and that's the American scenario, we would be focusing most of the supply chain in the Americas. South America continues to supply the lithium, but then it would be refined in the US and produced where the batteries, the cathodes and the cells are actually produced in the US. And so these are the 2 scenarios that we're looking at. Now, we realize that that the traditional scenario is by far the dominant scenario, but we're also really looking for, what happens if the US decides it does not want to be dependent on other countries for solids as it has been for liquids. If it decides, from a policy standpoint, if the US does ramp up lithium processing, then we there are some balances that we want to look at. And so what you're looking at here are 2 graphs focusing mostly on kilograms of CO2 equivalent for both lithium carbonate and lithium hydroxide. And what we're doing is we're listing the different areas along the supply chain that are producing CO2 emissions. Everything from electricity usage for refinement to truck and sea transport to the actual electricity source that is used for the refining itself. And what you're seeing here is on the graph on the left is for lithium carbonate and lithium hydroxide on the right. And bearing in mind that there are different y-axes here, different scales, right? So the lithium hydroxide has a much higher GWP impact, but there are a number of areas where changing the source and the supply chain can yield significant reductions in CO2. For example, in the lithium hydroxide, just based on the electricity mix between China and the US, where the US has a cleaner mix, we reduce the amount of CO2 for the electricity and refinement by over 50%. And there are other areas, for example, truck transport, looking at the traditional scenario, essentially evaporates to zero because there's no reason to move to use the transport for long distances. The impacts are a little bit more subtle on lithium carbonate, but you can still see areas where, particularly sea transport, which is a significant savings in GWP. Next slide. And so we do the same sort of process for cobalt. And here we're looking at the typical scenario where 80 to 90% of cobalt is mined in the Democratic Republic of Congo, the DRC. It is then shipped, it is actually trucked over to Dar es Salaam, put on a boat, and then shipped over to China where it is processed. And then it is made, and then if the cobalt is then made into product, shipped back to the United States where it's deployed. The second supply chain here is in the orange dash line, where the cobalt ore would be shipped over to Finland, where there is a process unit there. And then the third is where the refining is done in Canada at a facility that should be up and running by the end of this calendar year. The cobalt is then used in wind and solar in the US. So you can see it's really turns out to be, it's the transportation distances, the modes of transportation, and then the modes of electricity in the mix that is used to refine the materials that are then used in the product. And that's where you're really starting to see some differences. So, okay, next slide, please. And so the graph on the left is the base case, that's our China case. The kilograms of CO2, you can see that the numbers that are attached to each one of the little bars. For example, just trying to go through all of the processes for making cobalt does go through a lot of chemical processing, and that requires heat and electricity in order to make that happen. Under the two I would say treatments, one being the North American scenario and the other being the European scenario. In Finland, you can see the numbers there are relative to the base case. Okay, so the electricity generation that is needed for the North American case has a 93% savings of CO2 emission. So that's a huge benefit globally by processing the cobalt in North America. In Finland, it is a slightly lower savings, but it is still quite substantial. And then we're looking at other areas of transport. You can see that the transport, in some cases, actually higher going in a North American case, because we have to transport again the cobalt ore over to Canada in order to process. So there's a trade-off between where we do the mining, where we do the processing, where we do the incorporation. Next slide. Yeah, and here are the actual, those are the actual differences. So it's an 11% savings or so going to North America, and a 12.5% savings in GWP going to Europe. Next slide. Okay, so now we're going to do a direct comparison of CCGT compared to wind, and so when you do a life cycle analysis, you have a number of these. I think Gurjan mentioned that there are 17 different types of impacts, and there are ways to group these by both human health impact and by ecosystem impact. And what we're doing is we're showing a rundown of all of the different environmental impacts that are affecting ecosystems. So you have freshwater ecotoxicity, there's global warming potential, there's land use, marine ecotox, and so on. All of these affect ecosystems in some ways, in some way or another. And these bars are all summing the amounts in whether it's in kilograms of dichlorobenzene, whether it's in kilograms of phosphate production across the entire supply chain from sourcing all the way to end of life. And you can see that for CCGT, most of the impacts are under operations. And it's really not terribly surprising, because you're combusting natural gas, you're going to be releasing particulate matter, you're going to be releasing CO2, and there's going to be acidification from the combustion. So this is the area where, and of course there's water consumption almost dominates all of this, mainly because you're dealing with cooling of the towers, and so you're consuming water during the cooling. If you go to the wind, one of the things you'll note immediately is the difference between where the impacts are felt. For CCGT, it was because of combustion. For wind, it's because of all the processing that's needed to produce the materials. And so all of these orange bars are occurring during the actual, manufacturing and the processing of all the materials that go into the product. Next slide. And so one of the things that we're focusing on, which is I think quite unique, is that we are doing a time-dependent life cycle analysis as well. So, and this is where the front loading of impact becomes manifest. And it's particularly important for renewables, for wind and solar, because that's where all of the majority of the impacts are felt. Now, of course, land use is essentially manifested throughout the life of the facility itself, but all of the manufacturing and processing goes beforehand. So go ahead to the next slide. And so what we're doing now is we're looking at a per megawatt of land impacts and basically land use for a new power plant, with the greenish symbols being wind and the darker symbols being CCGT. One of the things you notice is that right at the beginning of the facility life, before electricity is generated, the impacts are actually quite high because we're using a lot of land in order to drill the wells, in order to deploy the wind turbines. And so, but as time goes on and we continue to generate the 3 terawatt hours a year, the relative differences between CCGT and wind diminish. And so this is where we look at how to normalize this. Are we looking at total land use, or are we looking at land footprint and land intensity as a function of how much electricity is being generated? Now, wind is kind of interesting because the way that land is impacted with wind depends on your perspective. If you are a bat, a bird, or a butterfly, then the above ground impacts becomes much more tangible and much more important. For terrestrial species, for most plants, and for for other creatures walking the earth, it's what they're focused on is the footprint of the turbine itself. So you can see between these two graphs here that there's a large difference in the impact when we consider the above ground, in other words, the length of the blades, versus the footprint of the turbine itself. And so there's about a fourfold higher land impact with the blade area, and it's usually 2 to 3 times the radius of the blade is considered to be the lateral impact. The largest land impacts are associated with, in this case, with sourcing, processing, and manufacturing, particularly for the CCGT. And then the asset life determines what those impacts are. So of course, if CCGT runs for 50 years, it's going to be generating that much more electricity, and it's going to have consequently a much, much smaller land use intensity. So these are some of the nuances that we're trying to tease out so that the general public and policymakers and companies can make better decisions when they're kind of thinking about how to frame their discussions with their investors and with the general public and with policymakers who are really, kind of altering policy decisions to sort of encourage or discourage certain types of electricity generation. Next slide. So obviously, wind and solar, the infrastructure for wind and solar has to be updated much more often than it does for CCGT. And so what we're showing here is the replacement of the hardware that is needed in terms of the GWP between wind, solar, and in this case, it's a PV, as well as with battery electricity storage systems, the BESS that are shown in there. And so you can see that after 2035, we have to start replacing batteries. We have to start replacing solar panels. We have to start replacing wind turbines. And so this begins to alter the annual scenarios of what the emissions are going to be. Now you can see the straight line for the CCGT is not surprising because we're continuing to combust natural gas. And so in the absence of a capture unit for capturing CO2, in the absence of new technologies that would be used to reduce the CO2 emissions and other particulates, that's sort of a straight line across the entire life of the facility. But you can see that, there are obviously areas where in some years, as we have to replace the hardware, we're going to be then incorporating and emitting CO2 back into the atmosphere. Next slide.
So Michael, let me just comment here,
Yes.
just to make sure that everybody understands. So as the note says here, this assumes certain life, for the different assets. But for example, let me point these little bumps going on here. These are for batteries. We're working with a, former student who is now working for a battery company, and their modeling when they are advising customers or developing battery stuff, battery projects. So batteries, those that are currently mostly being deployed, so lithium ion batteries of two types of chemistries, and every 5 years in the early life of the asset, there's something called augmentation to make sure that the battery capacity, installed capacity remains the same so that the facility can perform as designed. Because the batteries degrade and you need to augment that capacity. That's the terminology that is being used. And augmentation is a little bit larger in year 13 or so. So we have different assumptions about how long a PV solar facility will last. So our assumptions are just an example here, and we're trying to get more realistic numbers. One of the challenges that we have for solar facilities or wind facilities, given the relatively shorter history, are they going to last 20 years? Are they going to last 30 years? So we don't know that. There's not sufficient data yet. But we're looking for operating assets, what we hear from the industry and industry consultants, but also looking at manufacturers of these, solar panels and wind turbines and stuff like that, and their guarantees. One thing that we do not have here, inverters. We are now getting some information suggesting that the inverters may not last more than 10 years. So, and that is not in this chart yet. So once we, understand that better, we may have to, change some of these assumptions. If you have to replace inverters to maintain the, performance of the plant as originally designed, that might have certain implications on these impacts as well. Probably not a huge impact, but so we're going into that much detail. That's the key point. And this is just one set of assumptions. And we will have many, many scenarios like this. And also this is only one impact, just the global warming potential. The reason we're showing you the global warming potential, we have not finished our own analysis of solar and battery for all 17 of our impacts. So for solar and batteries, we are actually using the global warming potential from the literature, and in particular from NREL, National Renewable Energy Lab, which, those numbers and others numbers are more or less consistent across the literature. But for other 16 environmental impacts, we are waiting to finish our own analysis to have all these charts for all 17 impacts.
Great, thank you. And so, we're also looking at what is the speed of the transition itself. And here in this case, we're looking at two different cases. One is 100% renewable transition by 2050, and then the other is a much faster transition. And now, whether the US grid or whether the Texas grid or wherever becomes 100% renewable, we don't think it's terribly realistic, but there's a lot of discussion in the public realm about what is the proper mix, and are we going to truly decarbonize the entire grid, particularly in the US government currently. So we wanted to go ahead and look at this. And you can see that if we wait another 28 years or so for a transition to wind and solar with batteries, you can see that there's going to be a significant amount of tonnage of CO2 that's emitted from coal and CCGT, with a slow ramp up toward the end of that period from renewables. And if you go to the next slide, you'll be able to see a different scenario where if we do the completely unrealistic scenario of having 100% renewables in 3 years, which I don't think anybody would really believe is possible, but we're just sort of playing this out here. You can see that the coal and natural gas emissions are much lower, but that it has a significant ramp up on the renewable side. So we're clearly balancing the speed of the transition with what we expect the emissions to be. Okay, next slide.
Again, just to be clear, the way to read this chart, one-to-one comparisons, right? So we're shutting down all coal, which were generating 300 terawatt hours in 2020, or shutting down all natural gas, which was generating 300 terawatt hours, in 2020, and replacing them with one of these other alternatives, right? So this is not a portfolio; it's one-to-one comparison. And just to want to make sure that the audience is clear on that.
Okay, so I will send it back to you, Gurjan. Thanks.
Okay. So this is actually a good segue from the comment I just made, right? So in phase 2, rather than looking at one-to-one generation technologies, what we plan to do is actually look at an existing grid, let's say like ERCOT in Texas or any other grid, any part of the world, their current generation portfolio, and what might happen in 2030, 2040, 2050, just like we just showed, depending on our assumptions about transition pace. So, and here I'm giving you an example from an EPRI study. EPRI is the Electric Power Research Institute in US. And this is one of their modeling, and there are many different modeling exercises from Princeton and other universities, as well as consultancies, right? So, and there are different scenarios here: net zero, carbon-free, 100% renewables. Interestingly, they are not necessarily the same mixes. So we will look at these kind of scenarios from the literature and then do some dispatch modeling to make sure that perceived mix of generation is actually able to operate reliably. That is, electricity is delivered 24/7, without major interruptions. So then we're gonna look at the needs for transmission and distribution infrastructure. For example, one of the biggest debates today in the US at the federal level as well as regional system operator level is expansion of transmission capacity, which is really critical to integrate more wind and solar from locations where wind and solar resources are best, right? High wind speed and high solar irradiation and things like that. Oftentimes, those are distant from load centers, demand centers. And at least for 20 years, in the US, there's been a lot of discussion about green superhighways, transmission, grid kind of scenarios. So now there seems to be an increased focus, and utilities are getting on, these projects because they can build the transmission facilities, which will be included in their rate base, which is also good for their bottom line. But building transmission and distribution infrastructure to incorporate either remote wind and solar resources or within the distribution network, rooftop solar and battery storage, that's going to impact how the distribution network is operated. That has impacts on copper demand, for example, and then we have to add the life cycle analysis of that additional copper supply, for example. So that's kind of what we are going to do phase 2. And as a taste for that, and these are the ERCOT scenarios. And again, just looking at the global warming potential. And this is based on the ERCOT as the entity, system operator. They do a long-term system assessment every 2 years. So at the end of this year, there will be the new one. So this is from December 2020. So 2 of their scenarios is the current trend scenarios and then renewable mandate scenarios. So again, just looking at the global warming potential, under their current trend scenarios, if you look at over the next 30, 35 years, they're only forecasting through 2035. The rest is, our own extrapolation, of course, in this case. But as you can see, there is a difference between the two. And frankly, their renewable mandate is becoming more like the current trends 2 years after they did publish this research. So the next one should be closer to this. Their renewable mandate from 2020 might end up being in 2022 their current trend type of scenario, given the pace of development in West Texas in terms of wind and solar facilities. So, but this is one way to look at, different, impacts. As you can see in the current trend scenario, global warming potential from wind and solar is really, minimal, but kind of consistent over the years. But then in the renewable mandate, where there will be more deployment of wind and solar early on, the impacts are larger, but still much less than what's happening from the gas-fired generation. So again, this is one impact out of 17 we're looking at. So imagine, similar charts for all the other 16 variables that we will look at. And then finally, we will try to put all of these things together, building on existing work. As I mentioned, I have a podcast on this LCOE. So you can see the same chart in that podcast document that I made available as well. And then the report that podcast is based on. So levelized cost of electricity is not an adequate metric to look at to compare generation technologies, because we don't actually care about generation technologies when it comes to reliable service of electricity. We have to look at the grid itself. So, and that's what you see here. System integration cost is fairly well established in the academic literature. That those are the numbers that I use. And, years ago, a researcher from the Oxford Institute for Energy Studies in UK, for example, recommended the wind developers, which is the big deal in the UK, to bid firm contracts, meaning that they had to contract out for their backup generation rather than system providing that backup generation, which of course is going to have a cost implication. And now we're hearing that ERCOT is developing a similar approach. So anyone trying to develop in the future a wind farm in Texas, they may have to show either to the grid operator or the purchasers of the power, that they have contracts in place that secure their backup generation. So their generation is more akin to being dispatchable rather than intermittent. So that's, part of it. The research is fairly well established, as I said, and going forward, we're going to have to deal with that. Because as you may have heard, MISO, Midwest Independent System Operator, and ISOs in the western part of the country, they are, and National Electric Reliability Council, they are all issuing warnings for this summer that we may see blackouts in all of these systems, actually including ERCOT. And partially the reason is too much intermittent resources and too much retirement of thermal generation facilities in some of these systems, creating this risk if demand increases, maybe more than expected at certain days. So this reality is going to have to be handled one way or another. But still, system integrations cost doesn't get us to a full cost matrix from a social cost perspective. We need to include the cost of externalities. So our LCA analysis provides us with the foundation of environmental impacts that we can assign dollar values to. And with that, let me mention that we're looking for an environmental economist to help us do that cost analysis of the environmental impacts. Because as we showed you, all the environmental impacts are in kilograms of something, or liters of water, or something like that, right? Mass or volume units. But for us to talk about a cost of electricity, including social cost, we need to be able to come up with dollar values for those externalities. So let me just make that advertisement. We're looking for an environmental economist. So if anyone is interested, please reach out. So I think with that, we do come to the end. And currently, these are the sponsors of our project. And we are talking to mining companies and foundations to expand, and as well as renewable companies to expand this funding base. So hopefully we can do that, and we'll continue with the research, because as we do this research, we find out that there is a lot more to do. We showed you on the lithium and cobalt, But now people are asking us to do nickel and graphite, for example, right? We're only looking at CCGTs, solar, and wind, but now people are asking us to do nuclear power plants, with small modular reactors, geothermal facilities, carbon capture and sequestration. So there is a lot of work to be done if we can sustain ourselves. That's really the bottom line for now. Okay, with that, I think we'll open up to questions if there are any.
So Gurjan, I'll kind of help to kind of navigate some of the questions, and there are two. So the first question from Dominique is, he has a couple questions. In your study, did you account for technical evolution of the assessed generation technologies? If so, how did you include it? Excellent question. We have not included yet the innovation and how innovation is going to make a difference. Now, we are setting up all of our models to run in Monte Carlo mode, and we are looking at sensitivity analyses of all of the different connections between of the different processes, from all the way from extraction to processing and so on. And so what this means is we can project into the future and simulate what innovation would look like by reduction in CO2 emissions, for example, reduction in land use, reduction in water use, and that's how we intend to do it. So all of our models are set up to run in that kind of a mode. And the time frame is long. Do we account for changes in your background data? So the references, so we are updating the data that's in these databases with primary data using both company reports as well as peer review literature. Now, we know that the peer review literature has a delay of multiple years, and very often it's pretty much regurgitating data that's been used by other researchers, right? So, but companies are really reluctant to provide a lot of that kind of data. So we are going into the 10K reports that are issued as guidance to the SEC so that we can get raw data, as much of that as possible. We are also working with them. And so that's how, and in some cases, for example, we are using Tracy, which is EPA's environmental database that gets updated every 5 years through the US ETOX program. And so Gurjan mentioned we are, so the question was, are you planning to include other generation sources? The short answer is yes. We did not want to get too far ahead of our skis by promising geothermal, by promising small nuclear reactors, SMRs, for example, and other sources, including coal. And so, but these are things that are on the slate. Once we have the processing down, it's relatively straightforward to add a new type of generation technology. And so we're thinking about that now. And so, and also, do we have a reference to the presentation? I'm not sure exactly how to answer that, but I think that this is going to be posted. Rebecca, this will be posted, correct? Is that right?
That is correct.
Okay, excellent. And we are pushing to get papers. We're working on a number of manuscripts and a number of reports as well. And please reach out to us so that we can talk further. An anonymous attendee, do you think that material flow analyses can complement this research? And if so, how? Gurjan, you want to answer that?
Well, I was hoping that you would answer that, because none of us are engineers. Material flow analysis, as far as I know, is related to, I guess, the mining operations. But one thing I will say, maybe it will answer part of the Dominic's question as well. We're going to the primary sources, mining companies, as I said, some of the industry associations for copper, cobalt, and nickel, and some of the consulting firms that really do work with a lot of these companies. As Michael said, some of them are not willing to share some primary data from their existing operations, but we are kind of finding ways to get that data. So that's how we update some of the databases such as EcoInvent and others to the extent we can. And some of it, we have a mining engineer in our team, and he does make some bottom-up calculations for some of the mining processes. And we do try to incorporate newer best practices for mining companies that might be switching, from diesel engines to something else, or, less water usage and things like that. So I also take Dominic's question to mean for power generation assets. That's a great question, and Monte Carlo is one way to address that. But what the battery performance or the PV panel performance, wind panel performance, or CCGT performance will be in the future, beyond really 5 to 10 years, I think that's anybody's guess. But we're trying to address that potential improvement with Monte Carlo analysis. But I think, a related topic is we are going to do Monte Carlo also to account for regional differences. I mean, that's a really key thing. In some locations, you really cannot build CCGT. It doesn't make sense, right? There's no available gas. You would have to build pipeline infrastructure and so on and so forth. But similarly, in some places, it doesn't make sense to build wind or solar, right? It's just there's not enough wind, and solar, the plant will be very inefficient if you build it. So, but, in order to account for that variability, dependent on location, I think Monte Carlo is again gonna be one of the tools that we have. So the ranges that we're trying to come up is gonna be based on literature. So calculating of the externalities. In the meantime, if the person who asked the material flow question, if they can submit something maybe in more detail, we can try to answer. The last question that I see, calculation of externalities, are you following any handbooks or methodology for the calculation of the social externalities? As I said, we're trying to hire an environmental economist who is experienced in things like that. So, discrete choice theory or surveys, or there are methodologies like these. Neither Michael or I are experts in those. That's why we're trying to hire an environmental economist who can really apply the best practices, best methodologies to that. And I think that's the best I can say.
Yep, and I would add to that the methodologies that we're using right now to do the LCA generally is these are all ISO standard approaches. So we're following current standard practices and all the analyses that we're doing. The recipe, which basically helps to group and actually does the analysis of the outcomes from the LCA, that is also a very well used. It's called Recipe 2016. It's very easy to find on the internet. And that is a very much of a very, very common way of looking at LCAs for a wide variety of products, not just for the energy sector. Many of the outcomes from the Tracy analysis, which is used by EPA, actually focuses on toxicity to humans. So, and that is a standard approach that is being used across the government for a wide variety of different types of chemical emissions and chemical exposures. So from a social standpoint, those are the ways that we're doing it now. Now, if we're looking at things like sort of energy poverty and energy equality and environmental justice issues, we are aware of where the literature is. There are a lot of discussions about how to do this, but they have not yet really made it, in my opinion, to standard practices. But we are aware of the importance of this, and it is something that we are following so that we can incorporate that when possible. The phase one that we talked about is really meant to be transportable. So we could move our comparisons of wind, solar, CCGT, and others from West Texas in the US to Pennsylvania in the US to somewhere in Europe to somewhere in India, if we have the base information in terms of the wind, the solar, the access to natural gas, and so on. So we are trying to make that somewhat agnostic to the location, so that if we do choose to go outside of, in a particular area, whether it's rural, whether it's a peri-urban or whatever, we would be able to account for that. And I don't know if there's other questions. I
Well,
know
there's
we're
one more
very-
question.
Okay.
It's along the same lines. How would depend on China changing its own generation portfolio to renewables? It is a good observation. Power generation as the source of electricity for processing and manufacturing facilities is often a key contributor to global warming potential. Again, let me emphasize, we only show you the global warming potential for many of the charts because we haven't completed our own analysis of solar and batteries for 16 other environmental impacts. So power generation would be dominant for the global warming potential matrix, but not the others necessarily. So having said that, China transitioning from, 30, 40, 50% coal to something else, we will probably try to address that with scenarios. There are a couple of things there. If we're building stuff within the next 5 years, that transition is almost not that relevant because the existing generation portfolio, it is what it is. And the other thing is a lot of the processing for batteries or cobalt, I believe, or battery manufacturing in China seems to be happening in Mongolia. And Mongolia, there's heavily dependent on coal. And, we haven't seen any evidence that in Mongolia, there's going to be a transition from coal to something else. But it's a great question. And it points out, again, the multidimensionality of the space in which we are operating and how complex it is. So China might be building a lot of wind and solar, but maybe that's not necessarily where the battery manufacturing is taking place because they are trying to keep the cost low for that facility. So those are some of the complications we're trying to address either via Monte Carlo or scenario analysis, but we are aware of all of those things.
Great, and that is those are the questions that we have here. If there are any others, and again, we're sort of at the top of the hour, I guess we'll hand it over to Rebecca. We hope that this was helpful and useful and interesting. Please reach out to us if you have any further questions. Rebecca?
Sure. IAEE would like to thank Dr. Gershon Gulen and Dr. Michael Young for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we welcome you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.